Just a minute, sir. I will give you privileges.
Okay.
Yeah.
Okay.
Ramesh, sir, we can't hear you, sir. Please unmute.
Yeah, please.
Yes, sir.
ಈಗ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಅಂದ್ರೆ
ಕೇಳಿಸ್ತಾ ಇದೆ, sir. Now we can hear you.
Yes.
Yes, sir.
Yeah, I welcome Dr. Jyotishman Dasgupta to deliver second talk of today. He will be delivering a talk on Raman Spectroscopy. Professor Jyotishman Dasgupta is Associate Professor G at the Department of Chemical Sciences, TAFR, Mumbai. It's my privilege to read out a brief biography of Dr. Jyotishman Dasgupta.
I think-
Professor Dasgupta.
I think we can. I think, Dr. Ramesh, we can skip it in the interest of time.
Just very briefly,
Okay.
1 minute. Professor Dasgupta did his PhD work in the field of oxygenic photosynthesis from Princeton University, USA. Then he did his postdoc in UC Berkeley, and he has received many awards. In 2020, he has been included as the editorial board member of the very prestigious Journal of Physics Chemistry Letters, ACS publication. He has received many awards for his work. He is a very accomplished scientist. With this very brief introduction, I request Jyotishman Dasgupta sir to take over and deliver his talk. Welcome to you, sir.
Thank you, Dr. Ramesh. Thank you for organizing this lecture series from yesterday. And I'm sure students have benefited.
Yes,
And I just wanted to ask you questions before I start. Can you see my drawings here on
Yes,
the
sir.
slide?
Yes, sir.
Yeah,
Yes,
very
sir.
much, very much.
Okay. Okay. So thank you, Siddharth, for a very nice introduction to NMR and also chemical analysis using NMR. And also sort of telling everybody about the mode of detection of an NMR signal. It's going to help me a lot, and probably at the end when things become tight on time, and I can just refer to your talk. So, okay, so I think one of the things that I would like to cover is just the basic idea of Raman spectroscopy, and how we can apply Raman spectroscopy for various applications related to both chemistry and biology. I will miss out on the physics aspects at this point because I'm just a little bit biased because I'm a chemist, and I'm more interested in looking at molecules rather than solids. However, Raman spectroscopy has a huge application in solids, in looking at crystals, looking at extended systems. I'm not going to cover this today, but we can have a chat separately on how these are useful in physics questions as well. So let me start by saying there are three things that we are going to cover in this talk. What is Raman spectroscopy? Where can this be applied? And when it is necessary to be applied? Okay. All of these questions are pretty detailed and they sound like one-word questions, but they have a lot of scope of applications. And I will, in 1 hour talk, it's just not possible to cover everything. However, as you will go through this talk, you will see that Raman spectroscopy, as any other spectroscopic tool, applies optical interrogation. That means you have light coming into the sample and you focus the beam in some part of the sample and you collect essentially the scattering from that part using a detector. Of course, I've just shown a magnifying glass here. Don't worry about the magnifying glass, but there's a detector, and you can collect both in the spectroscopy mode. That means you are collecting intensity of certain vibrational lines, or you can go and sit on one of these lines and collect imaging data of a sample, of a chemical sample, of a biological sample. This is one of these images of a tomato peel in which these bright yellow regions are coming from a Raman scatterer, which is part of tomato peel's color, which is carotenoid. All tomato peels has carotenoid. You ingest it; it is the source of your retinal, metabolite, which is used, or the retinal, the metabolite that is used in your eye, the pigment that is in your eye. So carotenoids are a very good source of vitamin A, and these are carotenoids being highlighted by Raman spectroscopy, because carotenoids have huge Raman scattering, and you don't need to put a fluorescent marker to look at carotenoids inside cells. You can just do Raman spectroscopy and get the distribution of carotenoids inside cells. So it's just an example of what Raman spectroscopy can do. So let me just first say that spectroscopy is all about getting the right light source and detecting it. I just want to start with these two beautiful images that my students took in their private time. This is a picture that shows essentially what nature provides. These two pictures are sort of the idea that the source that nature provides is sun. And when you go around and look at nature in broad daylight, you get you can capture some beautiful colors all around us, right? You can see green color from maybe some biological growth. You can see very nice transparent water, the fluid on the surface. And all of this is a magic that nature creates by doing spectroscopy. Your eye is actually a detector of the spectroscopy that nature is doing. It has the light source, it has the material, and nature provides you with the material, all sorts of biological living and non-living things, the rocks here, the bed under the water, all are sources of very interesting light-matter interaction. And that's what spectroscopy is all about. It's light-matter interaction. You need to have the right light source, and you also need to have a curiosity about the matter. And hence, spectroscopy becomes a very, very satisfying business. You understand matter by shining light on it. But if you were to just think about it at the very fundamental level, when we learn in BSc and MSc, I hope all of you are doing bachelor's or master's, or if you could be school students, doesn't matter. We all know every material system has some energy levels associated with it. And this is simply because there is quantization of energy states in a material sample. And some of this you probably heard from yesterday's talks by Professor Sebastian and I am sure Professor Arunad, who have contemplated a lot on how you can interrogate energy states in material samples using spectroscopy. So the idea is any two-level system in this very complex jungle of energy states of any material sample or any matter can easily be looked at by shining light in the right resonance regime between the two states. So here is just a depiction of it. At the end, it's about a two-level system. Professor Siddharth Sharma has just demonstrated how NMR is done. Again, a two-level system usually, unless you have spin-coupled systems. But at the very core of it lies a plus half and a minus half sublevels of spin states, right? And you use RF frequency, radio frequency, as Professor Sharma elaborated, to create resonances between these two states. You can do the same kind of thing using visible light. And so these states will be replaced, instead of being spin states, these will be electronic states, okay? So now you can go between electronic states using visible transition, visible radiation, and or UV radiation or near IR radiation. All of these are possible energy sources that you would require to do spectroscopy and material samples. Okay, so the light source is important. Okay, Also is important is the detection. How are we going to detect spectra? Well, typically your eye does it in this image, which one of my students took in her visit to some place in India. This particular image is being taken by the camera the student used to record this image, right? The camera becomes a detector, or your eye becomes a detector when I watch this image. However, when we sort of do spectroscopy in a laboratory framework, or it means in a laboratory setting, we use things like cameras, like detectors, which can sort of read photons, can collect photons and read out in terms of some parameter which is easily recorded, and that could be current. So photon to current generating sources become detected. So those are important. One of the examples is a CCD. These are CCDs are available. Charge coupled detectors are available in your cell phones. So this is actually probably recorded from a cell phone or a big camera, whatever, and it has a CCD light detector. So light source, detector, and of course your material medium, your favorite object to look at. Those are the three things that you need to do spectroscopy. Now let's think about what the light source really means. Well, a light source is an electromagnetic radiation, okay? And any electromagnetic radiation which is traveling towards you has a very simple equation that you can look at. It's a wave equation, and it is actually characterized by if it's an electromagnetic wave, it is characterized by electric field and a magnetic field, which this amplitude A represents here for the wave equation, and a sinusoidally changing value of the amplitude. And this sinusoidal dependence is captured here very well by parameters which you know probably, all of you. The k vector, this is the wave vector. This is the frequency of this oscillation, which is characteristic of the frequency. That means if you have an RF, there is a characteristic RF frequency. If it is visible light radiation, there's a characteristic frequency associated with it. Sometimes visible light goes from 400 to 800 nanometers in wavelength, and you can convert that into frequency. So you have different kinds of frequencies which are characterized in this equation. So for all traveling waves and electromagnetic radiation, this simple equation represents the starting point of our understanding of what the light source is all about. So you have a wave vector which tells you the direction of propagation. You have frequency, which again tells you the oscillation frequency. And you have, of course, some sort of a parameter which is t. That means a time dependence to this entire wave propagation. All of this is essentially converges to what is the light source intensity. It depends on the value, the square of this amplitude, which is proportional to either the electric field or the magnetic field. The square of the electric field intensities, electric field amplitudes actually represent the intensity of light that you are shining on an object. Okay, so this is a simple framework for us to understand any spectroscopy. Okay? Any spectroscopy is related to the gaps that you are concerned about, what you want to measure. So if you were to measure spin resonances, this gap will be in the RF, so omega will change. If you want to measure absorption, emission spectroscopy, that means electronic states are involved, you will use visible light and IR light. Now, let's go to what is a Raman effect. Okay. Now, we all know that Raman made this principal discovery in India. But before we go into that discovery, let us just concern ourselves, what is the context of the Raman effect? So for any light matter interaction, you have four ways to think about the light matter interaction. There could be an absorption by the sample. That means the two energy states there is a resonance between the two energy states. You take the molecules from lower energy state to a higher energy state, that will always constitute an absorption event. Okay, so this is the basic absorption, which is, you can see it here, the body absorbs. Okay, in this case, a light source that's been shown in the cartoon. You can have emission. Okay, emission is nothing but release of radiation from an object after getting illuminated. So you can sort of look at this, you light up an object and you get emission at a different color. So you might sort of excite it with blue color, your emission will come with anything that is lower in energy than blue, and it could be green, it could be red. So emission and absorption are principally the most important light matter interactions that you can ever have. They're the strongest. They are the most allowed in all the cases. Okay, but there are weak effects like scattering, and Raman effect is an example of scattering. That means you can have interactions in such a way that you have radiation impinging on the matter, and the matter actually radiates back. So there is one photon that is coming in and another photon coming out. So this is essentially the idea of scattering. And scattering, as the word clearly tells you, hardly has very well-defined directions. Okay. However, we will see that not all directions are allowed, even in scattering. There are some rules that need to be followed. However, the word clearly tells this is different from absorption. You don't see any light coming out after the material absorbs light. However, if you wait for some time, you might have some radiation coming out in emission, right? So, and those could be in few directions, not in all directions, but few directions. However, in scattering, radiation comes in and goes out. Okay, so there is hardly a waiting time for the radiation to come out. So these are some of the three most important light matter interactions. But of course, there is reflection, without which you would not be able to see yourself in a mirror. This is also very weak effect as compared to absorption. But this becomes prominent if you make the surface shiny. Okay, make it smooth for all sorts of light to come out. All of these are, in a sense, characterized by the wave equation formulation. There is, in all of these events, when there is this light matter interaction, there are changes in the direction of propagation of the light. Okay, so if you have scattering, the light came from here, light went on some other direction, tangential direction. So there is a change in the wave vector. There is change in sometimes the frequency. The emission, for example, comes at a lower frequency. So the omega changes. You come with 1 omega, you have a different omega naught. You come with omega naught, which is high in frequency, and then you come out with a lower omega low with respect to omega naught, and that is a change in the frequency of light that is coming out. There is, of course, change in the electric field values of all these photons coming out after being interacting with the matter. And in some sense, there is also a change in polarization. This has not been captured in my previous slide in the wave equation. However, I did not tell you that the electric field can oscillate in a plane. Okay, and in certain cases, in light matter interaction, you change the plane of this oscillation. Okay, and so polarization is a term that characterizes that. So the polarization of the incident field can be changed after it interacts with the matter. So all these four things are important to detect in any spectroscopy. Not all are detected. You don't need to detect all of them, but you need to know that there are changes in some of them. In absorption, you do not change anything. there is an absorption event. In Raman, you actually change all four. Okay, in Raman you change all four. There is a change in the propagation of the light after it interacts with matter. There is change in frequency of light. It can be higher or lower frequency after it comes out from the sample. There is change in the polarization, and there is a change in the field values. Okay. So what is Raman effect? So as I say, it's a weak effect, but it was not until Lord Rayleigh talked about scattering in a more holistic sense in 1891 that we got a sense of what Raman effect could be. So scattering could be of two types. Okay, one is a Rayleigh scattering, in which the scattered photon have the same frequency. Omega remains the same. Omega does not change. So if you were to measure the scattered photons out of an object at the same frequency as the incident photons, you might see your detector might catch some of them. They're all coming from Rayleigh scattering, not from any other scattering, but Rayleigh scattering. And these are called elastic scattering because the frequency of photons, the incident frequency and the scattered frequency remains the same. You do not lose any energy to the material sample. However, Raman is inelastic scattering. That means you dump some energy on the molecule or you extract some energy from the molecule and you come out. The photons coming out sort of have higher energy or lower energy, and this is inelastic scattering. And as I said, Raman scattering, all four properties of light gets affected. You affect the direction of propagation, the frequency, the intensity of the radiation, and the polarization. So all of them become proxies of how to detect the Raman process, whether the Raman process has taken place or not. Any of them, if you detect, you might actually capture the essence of Raman. Okay. So let's now see how and why all these four get affected. So the first idea came from Raman himself, Sir C.V. Raman. He was working in his lab in Indian Association of Cultivation of Sciences in Kolkata, and in 1927, roughly, after he had read Compton inelastic scattering paper, he actually thought that this is actually possible to do the same scattering experiment with optical light. Okay, quantum scattering was done with electrons, but he thought that photons can be used as well. And so it was important for him to figure out ways to collect scattering of light from liquid samples, from solid samples. And with his PhD student, K.S. Krishnan, he set up a spectrometer that can collect the light source, a natural light source. So he used sunlight, and he focused the sunlight using a glass or some other means, and he could actually filter some parts of the sunlight to only have blue light coming and put that on a sample and collect in a spectrometer. You can see that this is the remains of the spectrometer that Raman used. You have the collimation of the light coming through, and you have a detector which was supposed to be connected here. I don't know if you can see my pen. Yes, somewhere here.
See, sir.
So this particular is the oldest Raman spectrometer that we know. However, it seems the Russians during that time, in very similar time, published a paper in 1928 by Mandelstam and Landsberg. They actually also sort of measured Raman scattering in liquids, and again a weak effect, but it is said that this discovery of Raman effect, of course the name came from C.V. Raman because it was all appreciated because the paper was published in Nature in 1928, a big journal. It has always been a historically big journal from UK, from United Kingdom, but the Russians also published in a small journal in Russia, where they had published the same effect. However, the name stuck with Raman. The basic idea was you focus sunlight after filtering it on a liquid, collimate the emission coming or scattering coming, and put it on a spectrometer. And that spectrometer will give you vibrational lines. It is the most important scientific work that took place in India in the last century. And I wish all students hearing today get inspired from Raman, that he did not have large amount of funding or large amount of manpower, people working with him to do this absolutely fantastic work, which led to a Nobel Prize in almost 2 years, one of the fastest Nobel Prizes that you will ever see. So even if you don't have money, even if you don't have people around with you, you can still pursue your love. And this is Raman's example is one of the shining examples that we have in our country. We don't have a lot of big scientific pedigree in terms of doing fundamental work and winning the most coveted prize in science, but Raman surely, even though it's a very weak effect, he shines more than everybody else. Okay? This paper was a 3-paragraph paper in 1928 that Raman published. It's the first thing that you should notice. It is a 2-photon process. It's not a single photon process. The Raman process is a 2-photon process. It requires both incident radiation and scattered radiation. So the material medium actually has 2 interactions, one with the incident and the other with the scattered photon. Okay, so it is part of 2 separate radiative processes. Okay, it was very clear from this paper that this Raman scattering effect was different from emission. He has clearly written here and I would like to highlight, some 60 different common liquids have been examined in this way, and every one of them showed the effect in greater or less degree. Is talking about the weak scattering effect with a different frequency. Okay, the effect is a true scattering and not a fluorescence, as indicated in the first place by the feebleness in comparison with ordinary scattering, and secondly by its polarization. So he was able to measure polarization, that is the plane at which the electric field is oscillating, as well as he was able to look at the frequency of the radiation coming out, and all of them were different. Okay? So how does one understand this effect? Let's go to the simple basics. The idea is in a molecular perspective. I have drawn it with respect to a molecule. We all know that molecules have electronic levels as well as vibrational levels, right? These are these vibrational states in the electronic manifold, right? Now, what is clear is that Raman effect, when it was first discovered, only measured spectroscopy of vibrations. Okay, and you can clearly see here that you can go from the 0th vibrational level, okay, and you can go to the first vibrational level by shining a light. So this is 1 and that is 0. This is V equal to 0, V equal to 1, the 2 vibrational states in any molecule, the ground vibrational state and the first excited vibrational state. You can go directly between the vibrational states and do spectroscopy. What is this spectroscopy? This is not Raman, this is IR spectroscopy. Okay, this is infrared spectroscopy. Why it is said IR? Simply because the color of the radiation that you choose to do this transition from this state to this state falls in IR. Okay, and this is, say, from 100 wave numbers to 4,000 wave numbers. Okay, so that is your IR range. It also tells you about the range of vibrational frequencies that you can measure in a model. Okay, you can go actually down to 10 wave numbers also. So I can remove one of the zeros. So 10 to 4,000 wave numbers. You can do a direct radiation and measure the vibrational spectra of a molecule. Then what is so different and so exciting about Raman? Well, Raman is not a one photon process. Raman is a two photon process. So what you do here is, and if I can erase this here, instead of going to the higher vibrational state directly, what you can do is you can impinge this radiation of any light, of any wavelength, of any frequency on the molecule, go to a virtual state, as we call it, go to a state in which the molecule's electron density is squished, is completely tormented for the time period of the radiation that is on the sample, and then immediately within few tens of femtoseconds, very small amount of time, 10 to the power minus 15th of a second, you come back down to a higher vibrational state, and that completes a Raman process. The Raman process is all about going from this vibrational state to this vibrational state through an intermediate. That intermediate did not exist in the molecule. You made it exist because you interacted light with the material and you created this virtual state, because in this virtual state the electron density of the molecule is completely different as compared to the normal molecule in its resting state. And once this is created, within no time, 10 to the power minus 15th of a second, a photon comes out. And that is a scattering process. This particular going in has a directionality, but when it comes out, it has no clear sense of direction. There will be some directional sense, I will talk about it, but it is scattered. It is scattered at a lower frequency. The frequency has changed. You see, you put in more energy and you get out less energy. This is the new L, the laser frequency. This is the scattered frequency. And that's your Raman-Stokes process. But you can also do this, that if your molecule is already excited to its first vibrational state, you can again give the same laser frequency, but you come down to a lower vibrational state at the ground vibrational state. In some sense, what you did, you extracted energy from the molecule and dumped it in the photon. Here, you dumped the energy in the molecule and excited the molecule. That's what the net effect is. You go from 0 to 1 vibrational level. You dumped energy into the vibration by going through laser radiation. In the anti-Stokes process, this is the Stokes process. In the anti-Stokes process, what you do, you of course give energy to the medium, but you come back, you scatter with a photon which is extracted energy from the molecule. The molecule was in V equal to 1, but now the molecule finds itself in V equal to 0 state. That means it has lost that energy. And so you will get a higher energy photon. Again, a Raman process. So Raman actually gives you two kinds of processes, one that is higher energy, one that is lower energy. And both are possible. However, the problem is, for every, when we think about it, one Raman photon is actually coming out in 10 to the power 7 incident photons. So this is really, really weak effect. Okay, so it is really, really challenging to do. You have to have 10 to the power 7 photons to create one Raman photon out of the sun. So detection wise, that's hard. But not only that, unfortunately, Raman is not the most favored scattering process. In 10 to the power 4 scattered photons from your sample, most of it is Rayleigh. Lord Rayleigh's beautiful theoretical description. Most of it is scattered at the same frequency. That means you go up with the laser frequency and come down with the same frequency. That is the most favored process. So it is one Raman photon in 10 to the power 4 scattered photons. So you can clearly see that even in the scattering process, Raman really is not really clear. So for all the scattered photons. So this is a very, very important number to think about. So Raman has very low cross sections. That means you shine light a lot and you get very minuscule amount of Raman out of the sample. But it is important because it tells you the vibrational spectra of the molecule. Okay? And that's how it works. You can really see that the Rayleigh transition is very intense. It has to be cut here in the spectrum. And you have the Stokes and the anti-Stokes shown here very nicely. The Stokes is very high intensity. The anti-Stokes are very low intensity. However, you can clearly see the line positions are the same. You are still measuring 0 to 1 vibrational spacings, whether you go from 1 to 0 or 0 to 1. Okay, so you're still measuring the same resonances, same vibrational resonances. However, you can clearly see the probability of watching a Stokes photon is very high as compared to anti-Stokes. And this is simple because you don't have molecules in higher energy states all the time. It is temperature dependent. If you were to populate, if you were to increase the temperature of your sample, you will populate higher energy states by simple Boltzmann distribution. And if you can populate higher and higher states, you can increase the anti-Stokes probability. So the anti-Stokes intensities are some sort of a thermometer of the sample. That means it can actually, you can calibrate the intensities of anti-Stokes to the temperature of a sample. You don't even have to put a thermometer, a physical thermometer to measure the temperature of a sample. You can just look at the anti-Stokes Raman intensities and you can calibrate to internal temperatures of the molecule. This is a very beautiful, illustration of measurement of temperature. So Raman effect, if you can measure, is really rewarding. Not only you get vibrations, frequencies, vibrational spectra, but you also can measure temperature. How weak is it? Well, it's not that weak that your eye cannot detect. Okay. In fact, your eye can be trained to detect single photons at the limit in a very dark room. So this is an example. This is one of my good friends, Professor Chandrabhas Narayana, who provided me this slide. You can blast your sample, a liquid sample, with blue light and watch using a filter that blocks the blue light, the Raman effect. This is a yellow light coming. That means this is a Stokes transition, because blue light is somewhere in between 450 nanometers to 500 nanometers, and yellow is close to 550 to 600 nanometers. So you can clearly see a Stokes shift. This is the Raman photons being detected by your eye, your naked eye. Okay, and that's an image. Actually, of course, I'm just cheating. This is an image by a camera, but you can see this, right? So you can actually see it if you hold the detector in front of your eye. You can see Raman photons, Stokes Raman photons coming out. So what are these talking about? Well, Raman is about looking at vibrational spectroscopy, and it's important for us to understand what do vibrations mean. Well, as I say in many of the talks, any chemical structure, any molecular structure, any biological structure, as it exists at room temperature. And it's always taking in the temperature, the energy from the bath. So if the molecules are in a solvent, the molecules are in gas phase, the molecules are in solid matrix, they always actually exchange energy with the room temperature. Okay, they're always constantly exchanging energy. They're always existing with at least the energy that is provided by the thermal surrounding, and that is KT, right? And I feel, and this is how I discuss vibrations, these are heartbeats of a molecule. Okay, these are the beating patterns of a molecule. The molecules are constantly moving. They're moving either by they're doing tumbling motion, rotations, they're actually moving around in a solvent, just doing translation, or doing vibrations. Now, why do I call vibrations at the heart of the molecule? Simply because every vibration is unique to a molecule and a set of molecules, okay? And it really characterizes the molecule. It's the heartbeat of the molecule because it's always beating in a periodic manner. So the way we think about this is these vibrations have to be quantified mathematically. These vibrations could be vibrations like a stretching mode between two atoms. It could be a bending mode as shown here, or it could be combinations of stretching, bending of different kinds, okay? And all of these are described by something called normal modes. For a simple system, normal modes are essentially description of motions, unique motions of the molecule, in which all atoms are oscillating across a central point, okay? And that could be the center of mass, okay? Now, normal modes are, for, we know that for any n atom system, we will have 3n degrees of freedom, right? Now, 6 of those go away if it's a non-linear molecule. 6 of them goes away as 3 translations and 3 rotations of the molecule degrees of freedom. 3n minus 6 are the number of vibrations in the system. If it's a linear molecule, it could be just 3n minus 5 because one rotation becomes regenerate. So if it was a very complex n atom molecule, the normal modes are 3n minus 6. Now, these are unique vibrations in the molecule. None of these two vibrations are the same, okay? And that's basically the definition of a normal. Of course, you can go back and read about it a little bit more, and we can take questions after the talk. The other aspect to the normal mode is normal mode always comes with a frequency. And the frequency of a normal mode is the most important observable in a Raman spectrum, the line position in a spectroscopy, okay? That's your frequency of vibration. It is given by a very simple harmonic oscillator approximation, which says that all vibrations can be projected to a 2-ball and a spring model, okay? 2-ball and a spring model, where the two masses are the atoms of mass m1 and m2, and the vibrational frequency is given by the force constant of the spring divided by the mu. Square root of that 1 by 2 pi is essentially in radians, the vibrational frequency. This simple formula is applicable throughout all vibrational spectroscopy, Raman, IR, whichever you want to pick. And this is the power of the spectroscopy. When you observe something, a line position in a spectrum, the omega actually gives a sense of what the force constant is in between two bonds, as well as the mass average of the two. This is called reduced mass, actually. Okay. So if you were to measure these frequencies, they will give you information about these two. Most of the times, you know what are the atoms connected. You don't worry about the nature of the atoms. You just don't know the force constant. And when you don't know the force constant, you don't know the bonding strength. So actually collecting vibrational frequencies become a way to chemically map a molecule. In fact, they become a chemical fingerprint. These stretching frequencies become important information for chemistry. You can clearly see a very strong bond like OH bond has a very high frequency of vibration, 3600 wave numbers. Of course, you can convert that into electron volts. You can convert that into your favorite energy units. Okay, you can convert that into joules or whatever you want. However, for Raman spectroscopy, we use wave numbers simply because it's easy to write these numbers without multiplying the Planck constant, okay, and the velocity of light. So wave numbers is nothing by 1 by lambda. That's your wave number. And energy is h nu bar times c. Okay. So you forget about this h and c. These are constants. So it becomes an easy scale to follow. It's just wave numbers 1 by lambda. Okay. So this in itself is a very nice way to think about it. 3600 wave numbers is OH stretch. NH stretch comes at around 3400. CH stretch comes around 3000 wave numbers. And all the rest come around 1100 to 1500 wave numbers. Okay. This is actually very conserved across, this range is very conserved across all molecules. So if you take Raman spectra or IR spectra, you can actually say what are the groups, functional groups in your molecule. You can characterize them. And you can also see what is the effect of vibrational frequency. See, a CC stretch is a C single bond C stretch is a weaker bond than a C double bond C stretch. Okay, this is a stronger bond. C double bond C is a stronger bond. So the CC stretch frequency is low in value as compared to C double bond C stretch frequency. Similarly, C triple bond C stretch frequency, because even a stronger bond, even shorter a bond, it is actually higher in frequency. It clearly shows that if I take the same mass of atoms, C and C have an effective mass of 12 in this case, 12. So all have the same mu, which is 12, and 12 by, actually it's 12 by 2, so it's actually 6. So if you were to just take the same reduced mass, you can see changing the electron density between the atoms changes the force constant. As the force constant increases, it actually increases the vibrational frequency. Similarly, now, however, you see what happens here. As you go from CH to CBr, your masses are changing of the atoms connected. So now the reduced mass gets affected, and reduced mass becomes larger and larger. The frequency actually becomes smaller and smaller. From 3000 wave numbers to CBr bond, which is 550 wave numbers, is really, really small in terms of the vibrational frequency. What is really interesting about these normal modes and the vibrations of atoms is also the fact that the frequency is connected directly to the time scale of the vibration. Okay, so this is an example of a molecule that we work in the lab. This is tetrathiophulvalene. I just like this example so much because you can clearly see the kinds of normal modes when the chemical species has changed. This is a bent structure of two of these cyclic rings, the sulfur-containing heterocycles. They are bent like this, as you can see in my hand. But when it becomes, when an electron is removed and it becomes a radical cation, if you are chemists, radical cation is one electron removed species, it becomes planar, completely planar and aromatic. In fact, the rings become aromatic. And this planar structure has a completely different set of normal modes as compared, sorry, this is the planar structure, is a completely different set of normal modes as compared to the bent structure. This is the bent, and that's the planar structure. You can clearly see the normal modes have changed. You can see that there was a normal mode, there is a normal mode in the planar structure purely coming from a C double bond C stretch, this particular C double bond C stretch. There's a simple normal mode that is stretching the this, and there is a very different normal mode for the ring C double bond C stretch. These are completely two different orthogonal modes, completely coming at two different frequencies. But when you have the bent structure, that means the original structure, when it is not planar, these are mixed. You can see you can't find a pure C double bond C stretching mode here anymore. They're all mixed with each other. Okay, so depending on the structure of the molecule, the normal modes are different. Depending on the conformation of the molecule, the normal modes are different, and the combinations of these motions become different. They also talk about symmetry of the system. Okay, so these normal modes also talk about symmetry of the system. Apart from this, it's very interesting to see that we can convert these numbers in time scales of motion. So a 27 wave number bending motion of this molecule, 27 wave number, 27, very low frequency, can correspond to a time period of 1.2 into 10 to the power minus 12th of a second, picosecond. It's 10 to the power minus 12th of a second. So that's how fast the molecules are vibrating all the time at room temperature. Okay, 10 to the power minus 12th of a second. Very, very important number. This again has a beating pattern of a different normal mode, has a different beating pattern. Every normal mode has a different frequency and a beating pattern. So this is 78 wave numbers corresponds to 420 femtosecond. It's even faster. So 420 femtosecond means 420 into 10 to the power minus 15th of a second. Femtosecond is minus 15. Okay, so or you can write this as 0.4 into 10 to the power minus 12. Okay, I can convert that into minus 12. Okay, So this again becomes a very interesting number to know. Vibrations are taking place in few femtoseconds to picosecond time scales in your molecule. And those are the vibrations being captured in a spectroscopy measurement. This is crazy because you can watch these vibrations in your Raman spectrometer at whatever time scales. In seconds, you can collect data and you get the information about a motion that is taking place in 10 to the power minus 12th or minus 15th of a second. And that is really the power of spectroscopy. Okay, so it's important to have this information with you. So normal modes not only talk about vibrations or the symmetry of a molecule, the vibrations of a molecule, but they also talk about time scales at which the beating pattern is taking place in a molecule. Now, of course, you can get these vibrational spectra from either IR or Raman measurements, but of course, I'm going to quickly skip this because I've already taken a lot of time going through the basics. But IR and Raman are always at odds with each other. Okay, you might have a question: which one should I take? Well, it's very simple. Raman is, since it's a very weak scattering phenomena, so IR spectrometers are more popular. You can actually do IR measurement for any sample. It's very simple. It's an absorption measurement. However, it's very important to understand that there are only certain vibrations that can be seen in IR, and there are another set of vibrations that can be seen in Raman. What actually is the difference? IR actually is an absorption measurement, and it is done in the linear scheme. That means you have a transmission geometry. You impinge light on the sample and you detect whatever was absorbed. Okay, you have a shadow of coming from the sample. The sample actually casts a shadow on the source. Okay, and the shadow is what you collect. That's your transmission spectrum, right? Because you collect only those, you collect everything else, but you have missed out some photons, so you plot the missing of photons, and that's your spectrum, right? So you collect the shadow, that's what I call it. It's the absorption of light. In Raman, however, this geometry could be completely different. You need not collect the Raman spectrum in the same direction as the laser source. In fact, you don't want to, because Rayleigh is so strong. The elastic scattering is so strong, it dominates, and you don't want elastic scattering to dominate, as well as you don't want the original illumination to dominate, right, in your detector. So you do at an angle, usually a 90-degree angle, okay? And that's how you place the detector, and you get scattering. Since the scattering is all over the place, you collect the Raman scattering from this side. What does it depend on? IR depends on changes in dipole moment of a molecule, and hence IR intensities are proportional to changes in dipole moment along a vibrational mode. So if the vibrational mode is stretching, okay, and you are stretching and the dipole increases while you are stretching, it will be an IR active mode. Okay. However, if the stretch does not lead to increase in the dipole moment, all bets are off. IR is inactive in that molecule. However, in Raman, it's not the change in the dipole, the permanent dipole in the molecule, but it is change in the polarizability. And I mentioned this at the start of the lecture, that when I impinge light on the sample, the electron density gets squished, okay, because there is electric field that you're impinging on the sample, and the field sort of distorts the electron cloud. And the alpha is a term that signifies the distortion. It is essentially polarizability. It's called polarizability of the material sample. And what does it depend on? It basically depends on intrinsic parameters of the molecule, completely intrinsic, how the bonds, how electron dense the bonds are, and how the bonds are being connected to each other. Okay, the atoms are being connected to each other. Again, if there is no change in a stretching, if there is no change in polarizability, then that will be Raman inactive mode. So let's get a feel for what this means. Okay, So this is a molecule that is a very simple molecule. In this case, we have taken a CO2 molecule, and you can clearly see in this very simple linear molecule, you have an if I were to just take dipole moment change, then a symmetric stretch will lead to no dipole moment change, because whatever is being pulled here, the bond length change here is symmetrically done here, and so the dipole cancels out, and there is no dipole change at the mean position, and hence this IR mode is inactive. Okay. However, if you look at Raman, okay, it is the squishing of the electron density. What is the electron density? The electron density is all over the place. This is a CO. So this is double bond O. If I put a large electric field coming from the incident radiation, and if this stretching is being taken place, then the stretch changes the polarizability of the molecule, because the electron density is getting narrower at the center, and it's being pulled along this axis, and hence as you pull along, there is a non-zero change in the polarizability, and hence this is a Raman active mode. In fact, all totally symmetric modes are Raman active. All totally symmetric modes means all vibrations that preserve the symmetry of the molecule are always Raman active, and that is shown here. You can clearly see that this particular stretching mode is Raman active, but in IR it's inactive. So if I want to detect CO2 and especially look at the symmetric vibration for some, if the molecule is sitting on a surface, if CO2 is sitting on a catalyst surface or binding to a catalyst, a molecular catalyst, a symmetric vibration tells, the changes in the symmetric vibration frequency tells the binding interaction, and that is very sensitive. So Raman will be the way to look at it. In fact, people have been using Raman to look at CO2 interactions with iron catalyst that can be used for, say, CO2 reduction catalysis. Okay, so this gives you a feel for what polarizability is and what dipole moment changes. In fact, you can clearly see all the other modes, the unsymmetric modes is dipole active, and hence you see IR coming from both of them. However, for polarizability, these two modes are polarized. They symmetrically change the polarizability. The polarizability, as they call it, the ellipsoid, the polarizability ellipsoid does not change its volume. And no change in volume means it's a symmetric potential, and you do not see any Raman activity for these two modes. So for this CO2 molecule, it's beautiful. There is one Raman mode that is active and two inactive, but IR, two active and one inactive. It's very complementary. This gives you a feel for what the polarizability is. So now the question is, of course, you have some sense of what Raman effect is. You know what the frequencies are changing. You know what polarizability is. You know that the intensities are weak. So let's now ask the question, where is it really applicable? Well, as I said, you can identify chemical species, functional group analysis can be done. You can also look at crystals of molecules, and you can look at crystal phases. Crystal phases means if the molecules are getting packed slightly differently, you'll have a different lattice parameter. And in fact, in solid states, for example, a manganese fluoride crystal can have different phases that will change the manganese fluorine distance, and that will change the vibrational frequencies, and hence you can sort of identify crystal phases and facets using Raman spectroscopy. However, it's not just the vibrational line position that is important. The frequency does tell you about chemical species and phases, but it's also the line shapes, the widths, and the intensities that talk about really a lot of information about the sample. Local order can be looked at using widths of the peaks. Heterogeneity of the sample can be looked at by using widths of peaks, as well as you can look at intensity of peaks to get information about the molecule. So let us actually go through a known Raman spectra of a molecule. If you look at this molecule, maybe you will not be able to predict that this is coming not from a very simple set of a simple molecule, but it's a very complex biomolecule. In fact, it's a protein. This is the size of this molecule. It's called rhodopsin. It's in your eye, and it harbors vitamin A, modified vitamin A chromophore, the retinal chromophore. Okay. So this particular Raman spectrum is of the retinal part of this molecule. It clearly tells you why you should do Raman and not IR. If I were to do IR on this big molecule, all the vibrations will be visible. All the vibrations. The vibrations are coming from the protein, the vibrations coming from the membrane in which the protein is put together. Otherwise, the membrane won't be stable. The vibrations of all residues of the protein. Professor Salma actually talked about NMR of all residues of the protein. In fact, IR does the same. You can actually look at all oscillators in the protein, but you don't want to because it becomes very congested and complicated. And Professor Salma told you that multidimensional spectroscopy can be done to sort of disentangle all the signals, the spin signals from a sample, right? But using Raman, you actually selectively can look at just the vibrations coming from retina. How is that? It's very interesting. It's called resonance Raman feature, which is only allowed because Raman is a 2-photon process. IR is not a 2-photon process. It just goes and matches the gap between the vibration states. But since Raman can take place from any kind of photons, right? You can use visible photons, you can use UV photons, you can use NIR photons, you can use X-ray photons to do Raman spectroscopy. Okay, that's all you care for. Okay, so since Raman provides you that handle of tunability, you can actually excite your molecules with visible light, which is in resonance with this retinal absorption. If you do that with that retinal absorption, you get this beautiful selective Raman spectrum of retinal in its 2 different states. Okay, and these are the 2 cis and trans states of the retinal once the light activation is done. This is how your eye actually detects light. The retinal changes its geometric configuration from a cis to a trans, and it actually gives a signal to the neurons that I can see the photon now. I can see light. Okay, so so this is essentially a pure Raman spectrum of this molecule. Just the molecule buried in the protein in such a complex environment. Okay, well, how did we get it? We use the laser radiation, which is in resonance with the absorption of this molecule, and this molecule absorbs at 500 nanometers. So if you bring a laser light of 500 nanometers, you will get this Raman spectrum. It's only the Raman spectrum coming from chromophore, and rest of it can be ignored. Okay, so this is the idea. So there is great selectivity in Raman, poor sensitivity, and we know what we are measuring. All the Raman measurements are in the time scales of few femtoseconds. It's a scattering process. Okay, so apart from this, it's actually important to also not just think about the sample, but also what can you do since there's great selectivity and tunability in the light source. What can you do with the light source so that you can enumerate more about the sample? You could change and play with the polarization of light. Okay, so there is a very simple experiment that you can do with Raman. You change the plane of the electric field oscillations. So you can choose a polarized radiation. That means radiation in which electric field is polarized in one single plane, and your electric field only oscillates in that plane. It interacts with the sample, and when you collect the 90-degree scattering of the sample from the sample, you will see some of these. The scattered radiation has some of these the polarized radiation depolarized. It actually starts oscillating in 90 degrees of that plane, and this is essentially called depolarization. That happens because scattering depolarizes the original illumination polarization. And you can collect these electric field oscillations by just positioning a polarizer. The polarizer can collect intensity of light only from one plane, and you can rotate the polarizer to allow for another plane. So you can collect the information of which plane the electric field is oscillating by just blocking or allowing that polarization. And that's what an polarizer here does. It actually eliminates one kind of polarization. So you can in principally see if what is the ratio of the radiation coming in this plane, oscillating in this plane, which is called parallel plane, versus the perpendicular plane. And if you plot the perpendicular by parallel, this ratio is called the depolarization ratio. Every Raman line has a depolarization number, simply because each of these Raman transitions are normal modes, and normal modes are vibrations of the molecules. And as I said, all totally symmetric vibrations are Raman active. All totally symmetric vibrations actually give to polarized Raman radiation. Okay, that means for all totally symmetric molecules, all totally symmetric vibrations, the value of perpendicular to parallel, perpendicular part is very, very small and parallel is large. That means if you were to polarize the radiation, it will hold on to its polarization in a totally symmetric vibration. But if you polarize and look at a non-totally symmetric molecule, that means it does not conserve the symmetry of the molecule, vibrations that don't conserve the symmetry of the molecule, you will start seeing perpendicular polarization. You will start scattering out. You will start depolarizing your incident radiation. And you get, for non-totally symmetric values, vibrations, you get values of 0.75. Versus for totally symmetric, you can go to 0, okay, almost 0. This is important. It's shown here very nicely. This is again a Raman spectrum of CCl4. You can clearly see that the major mode that is Raman active is a totally symmetric mode. CCl4 is a tetrahedral symmetric molecule. So if I were to just play the animation again, you can clearly see this particular vibration is conserving the tetrahedral symmetry of the molecule, and hence it is highly Raman active and highly polarized. You see how polarized it is. This is data collected at parallel mode intensities, and this is perpendicular. So you can clearly see the perpendicular mode is quenched, the parallel is highly intense. This has a depolarization ratio of 0.02. It tells you about the symmetry of the molecule, which vibration is totally symmetric. Immediately a depolarization experiment can tell you. You clearly see these two vibrations are not totally symmetric. In fact, they break the symmetry of the molecule. Again, if I show, they are breaking the tetrahedral symmetry. And this particular, all of these, by the way, are non-dipole. They're all dipole conserving, while this particular mode and the nu3 mode is not dipole conserving, and so it's actually Raman inactive, almost Raman inactive, but IR active. Okay, so again, a depolarization ratio of 0.75 is held here because it's a non-totally symmetric. Okay. So these are the ways by which you can actually look at the symmetry, the changes in the symmetry of a molecule. A parent molecule can lose its symmetry by binding to a surface, by binding to a catalyst, or being there in a biological milieu. You can actually use Raman depolarization measurements to look at how the changes have been affected. Okay, and they also talk about essentially the orientation of the molecule on a surface. So if the molecule's dipole is oriented with respect to the field polarization, there will be enhancements. If it's along the field, there will be enhancements. If it is perpendicular, you may not see a Raman transition. So this is a very important characteristic of a Raman spectrum, the depolarization ratio. Okay. Now all of this has to be put together in a lab. So just to a simple description of the apparatus, And I know I'm running out of time, but I started, I think, at 12:30 something, 12:34 or something. So is that okay,
Yes,
Dr.
sir. Yes, sir.
Ramesh?
Another 10
Yeah,
to 15 minutes you can continue, sir.
yeah. So are there any? So let me actually finish this part and then I'll go to the questions, because I know this is a huge field and it takes time for people to sort of appreciate what they're seeing. So this is a Raman setup that you can build in your own lab. It's actually a simple idea. Raman spectroscopy is as simple as emission spectroscopy. You have the same exact setup. You take a laser. Um, Take a laser. You need some control on the laser polarization, because depolarization measurements are important in Raman. So if you can prepare your laser, which is a polarized radiation, that's great. Then you can take some mirrors and put the polarized radiation through a focusing lens onto the sample. Now this sample will scatter light in all directions. So you see there is perpendicular and parallel directions that you can measure. You can have a collection lens because you want to collimate. Okay, so you are focused it on the sample. So now it is coming as defocused. So the collecting lens will collimate, and then again the collimated beam will now be focused back to the slit. Okay, so this lens will focus it on the slit. Before it goes into the slit, there is again a polarizer that will allow for clearly distinguishing what kind of intensities you get from perpendicular and parallel. So this is called an analyzer. It will actually can be rotated, and the same Raman spectra can be plotted both in perpendicular and parallel mode by quenching one of the directions. And you can also have a polarization scambler. If the modes are already polarized in some sense, then you can sort of, for detection, there could be a polarization scambler. Now, you can have an entrance slit. In the entrance slit, what you have, you can have a PMT, a photomultiplier tube, or you can have a spectrometer with a regular grating-based spectrometer with a CCD, okay, a CCD chip, okay, just like in your camera, in your cell phone. So now this, of course, these are photon to electricity conversion devices. So you need to connect it to a computer that will actually watch how much current is being generated, and there will be a sort of a current to intensity calibration done by a photon counter, and that can allow you to plot the intensities, and the intensities will be displayed in your computer as Raman lines. So that means you will get for all sorts of, so if you were to incident radiation at 532 nanometers from the laser, you will get some resonances at Stokes frequency shifted. Say, for example, 540 nanometer, you will get some photons at 560 nanometers and 570 nanometers, and so on and so forth. Now, you do a simple calculation that you subtract the energies of these two radiation to get in wave numbers what these modes are. So you can calibrate it to wave number scale, and you get, say 150 wave numbers, or say 500 wave numbers of this for 540, and so on and so forth, say 2000 wave numbers and so on. So you can easily calibrate it. The computer does it for you. You just tell the line source, radiation source wavelength, and it will collect the data and do the subtraction for you, and you get a Raman spectrum, okay, in wave number calibrated axis. It's called Raman shift, and you can collect either the Stokes or the anti-Stokes depending on the filters that you can choose. The filters are not shown here, but you can choose sort of a notch filter which blocks the incident radiation pretty well, and just allows all the scattered radiation which are Stokes shifted to go in, okay, into the spectrum. Okay, so coming back, so that's your detection part. That's how you do it in the lab. Now I'm going to quickly browse through some basic ideas of how mathematically you can understand Raman spectroscopy. I won't have time to go in details simply because I think I need to show a little bit of examples of Raman. spectroscopy applied in relevant cases in contemporary sciences and chemistry. But just a very simple idea. I have already told you what incident radiation does. It creates a polarization. That means induced dipole. This is nothing. Polarization is nothing but sort of polarizability is given by alpha, but the polarization created, macroscopic polarization in the sample is created by the light, and that is given by, it's proportional to the polarizability. That means how best you can polarize, how much you can polarize a material system depends on the material system's properties, but polarization also depends on the electric field that is used. That means the incident radiation, how much field, how much intensity have you put in. So it goes linearly with electric field, and this alpha can actually be expanded in terms of the molecular parameter, which is a normal mode. So you can actually describe polarizability in terms of the normal mode vibration. That means the vibrations are taking place all the time. How do these vibrations change the electron density of the bond? Okay, so that is given by this term. If you were to, this is a Taylor series. So if you were to just take the first two terms, that means the zeroth order polarizability, which is just a simple number, and the first order polarizability term, which is the derivative of polarizability with respect to the change in the normal mode length scale. Okay, the length scale of the normal mode change, that is the derivative of the polarizability multiplied by the polarizability vector. Okay, the direction or associated normal mode. That in itself describes the overall polarizability of the sample. If you were to take a product of this vibrational frequencies, this is your non-stationary molecule, how it oscillates. The length of, say, if it was a simple stretching, the length scale would be defined by the bond length. So the bond length, while the stretching is going on, is described in time by this simple expression. It's a sinusoidal oscillation of bond length is given by the mean bond length times the cosine function, and this is the vibrational frequency of the bond of the stretching mode. And that in itself, if you take a product with the electric field oscillation, which is E, that means you take a product of E naught of E, which is E naught cos omega 1t times this particular factor qk, you can clearly see that P1 can then be expressed as alpha, which is these two terms, the alpha 0 plus the alpha prime times qk times the E, which is E naught times cos omega 1t. Okay, that's your laser frequency. So the qk has a sinusoidal dependence in vibration. So these two terms, when you multiply, there will be a cosine multiplied by a cosine. Cos theta times cos phi is given by sine theta plus phi plus sine theta minus phi, right? So those two terms will emerge, and those are the emergence of the Raman terms, the Stokes and the anti-Stokes terms. Those are the frequencies. So the new frequencies are being created. One that is a summation of the two, which is an anti-Stokes frequency. That means omega k plus omega 1. So that is here. This is the anti-Stokes frequency. So new frequencies have been created in the material system, as well as omega 1 minus omega k. That means the incident radiation minus the vibrational frequency. This is the Stokes shifted line. So this is in the macroscopic polarization. The macroscopic polarization of the material system then actually leads to the Raman photon coming out of the system. So that is the classical theory of Raman scattering. I think I will just go through this today. There is, of course, a quantum mechanical version of this. I will not have time, unfortunately, to go through that today, but I'll give you the brief idea. Now, what this also tells you is that if I were to look at this, the intensity of these lines, okay, is actually proportional to how large this derivative is, the alpha prime, d alpha by dq. So the polarization that you create, the Raman polarization, is directly proportional to alpha prime. That means the more the polarizability, the more the intensity of the Raman lines. Alpha prime with respect to alpha naughts are typically in the order of 10 to the power minus 7 in most of the molecules. That is why it is such a weak phenomenon. So if you make this larger and larger, you get larger Raman scattering. To get a sense of what alpha prime really means or alpha really means, in complex molecules, alpha is not simple, it's not a vector, it's actually a tensor, okay? And that tensor is given by 9 elements, which is the polarizability tensor. This is the polarization direction. So that's your macroscopic polarization, that's your vector, that's your electric field that creates that macroscopic polarization, and that is related by this 9 element matrix, which is called the polarizability tensor. It is actually an ellipsoid. It has values in 3 principal directions and also in off diagonal directions. So to visualize this is slightly complicated, but I'll just tell you that the polarizability tensor part is the most important part of understanding Raman intensities. Okay? And this is actually worked out quantum mechanically by 3 people, Kramer, Heisenberg, and Dirac, who actually worked out the mathematics and came about with this very simple expression for polarizability, which actually has a simple thing to look at if you were to understand this. This is the first photon interaction, this is the second photon interaction, and this is the denominator talks about the energy matching criteria, that if your frequencies, the incident frequency matches the frequency of resonance, an electronic resonance, then this entire term actually becomes, this part becomes 0 or close to 0, and this blows up and the polarizability really increases. And this happens in resonance Raman. That is what I exactly mentioned when I talked about looking at retinal proteins inside a protein. Retinal proteins, the retinal chromophore inside rhodopsin protein. Okay. So, so now I'll just quickly go through the rest of the slides because there is hardly any time. We can talk about, take questions afterwards. So where Raman is typically used, it is absolutely necessary in industry, in the diamond industry. If you were to think about quality control of diamonds, whether you have a clean diamond or not, or you have a diamond which is artificial, you can clearly measure from a 1328.7 Raman line. This 1328.7 Raman line is characteristic of a genuine diamond. Okay, so you can clearly go to a Raman spectrometer if you want to check how good your Raman, your diamond is, and you can collect a Raman spectrum, and this will be characteristic of your diamond. There are other ways to use Raman spectroscopy, but in nanomaterials, Raman spectroscopy is again useful. This is one example where carbon nanotubes, which are used so much now in catalysis and other kinds of applications, have specific Raman frequencies that you can sort of collect and get information of the structure of the carbon nanotubes. This is one example. There is a mode, a normal mode called radial breathing mode. That means the carbon nanotube goes like this, breathes. The entire carbon nanotube cylinder increases in size. The entire cylinder increases in size. It's a radial breathing mode. And that radial breathing mode can be correlated to the absolute diameter of the carbon nanotube. So this is at 250 wave numbers. This is close to 250 wave numbers. If there are changes from that, it can go from 150 to 250 wave numbers. Any change can be correlated to the size of the modes. So size of the carbon nanotubes. So suppose a 20 nanometer carbon nanotube will have a radial breathing mode at 250 wave numbers. Then a 50 nanometer carbon nanotube has a radial breathing mode at 150 wave numbers. So these are some of the very, very interesting changes that you can correlate to structure of nanomaterials. This is an incredible technique to look at and characterize your sample. Also, you can do biological imaging, where you can actually go and look at, you don't even have to use a fluorophore. You can just use Raman spectra to sort of label-free watch lipids in your or carbohydrates in your cellular architecture, and they can give you beautiful Raman spectra, and you can give information of the cell, how the cell is working. In fact, there is a lot of work now being done to use Raman probes, that means sending molecules which are large Raman cross section and going to different parts of the organelles to look at how the cell works, how the cell metabolizes things. So label-free imaging can be done in biology, okay, using Raman spectroscopy. So what we have learned today pretty much is Raman spectroscopy is actually giving you the chemical fingerprint of a molecule. So you can actually characterize a molecule, and it is fantastic because you can get vibrational contrast. That means you can look at one set of molecules in a pool of many molecules, just like in the rhodopsin case, and get enhancement of that molecule and contrast with respect to other molecules. Okay, because a set of one molecule, a unique molecule, we have a unique Raman spectrum. There cannot be another Raman spectrum that matches that molecule's Raman spectrum. So there is a vibrational contrast. So you can do spectroscopy and you can image molecules. You can also do look at the time scales of Raman. Essentially, you can sort of watch a chemical reaction and watch the reactant and reactant to product getting converted by just following the Raman spectra of the molecules. But you can clearly see the problems with Raman is poor sensitivity, and of course scattering is not an intuitive phenomenon at all. So these are the typical Raman cross sections. Fluorescence cross section is 10 to the power 14 times larger than Raman cross section. So one of the things that Raman spectroscopies wonder about is enhancement of Raman spectra. Typically, if you have large electron densities like pi conjugate systems, they have large Raman cross sections, but you don't always have large Raman cross sections. So there are ways to enhance Raman spectroscopy. I'm going to quickly go through this. There could be electronic resonances, as I mentioned. You switch on the light in resonance with an electronic transition. You can get resonance Raman enhancement. There could be surface enhancement. If you put it on close to a surface, your molecule close to a surface, and the surface has a resonance effect, where the surface could be a silver or a gold sphere, and the gold has a plasmon or a silver has a plasmon. If you excite the plasmon, the molecules near the surface get enhanced, the Raman scattering from the molecules near the surface get enhanced, and that gives you surface enhancement. You can also do tip enhancement, where you can bring a very, very sharp tip near the molecule and interrogate the molecule. The tip has a large voltage bias, then you can create a large electric field near the molecule, and you can also measure enhanced Raman signatures. This is the resonance enhancement idea. The virtual state becomes the resonance state, and the enhancement goes through orders of magnitude, 10 to the power 4 to 10 to the power 6 times. Okay, and I'm not going to talk much about it, but I'll just clarify that when you do resonance Raman spectroscopy, unfortunately, fluorescence also comes through. So if you were to do Raman spectroscopy, resonance Raman spectroscopy, remember that your laser radiation, if you put in higher energy as compared to the absorption feature, your Raman spectra will be buried in the absorber's sphere of influence. So your Raman spectra could be depleted because of self-absorption. However, if you were to be too away on the red side, that means on the lower energy side, then emission will be accompanied with your Raman spectrum, and your Raman spectrum will be on top of the emission. but it's actually sort of a balance that we have to strike. We cannot be too high in frequency or very close to the emission. You might want to be a little bit close on this side. Close, it's called pre-resonance. If you were to excite somewhere here, you get the best of both worlds. You get a resonance, nearly the resonance enhanced spectra, and you get rid of emission. Okay, I'm just going to tell you that you can do this based on the resonance enhancements. You can actually selectively probe molecules. This is an example from our own lab where we looked at carotenoid molecules in a tomato peel. The carotenoid molecule in a normal tomato displays this molecule lycopene, which is red in color, absolutely red in color, has a geometric sort of all trans geometry, but when you actually deplete this particular tomato from one enzyme, this lycopene never forms and it becomes pro-lycopene, and this gives an orange color. So we can actually watch from a tomato peel which part has pro-lycopene, which part has lycopene, simply because you can be in resonance with the lycopene more often and off resonance with pro-lycopene. So you can actually sort of watch this under a microscope and image the tomato peel. These bright spots show lycopene deposits. These bright spots on the other side on a mutant tomato peel shows pro-lycopene deposits. And these are two completely different carotenoids. And what you can do is you can sit on one of these peaks and create an entire image out of this. So this shows the distribution of the molecules in the carotenoid field. So again, a very important application of Raman is selective chemical imaging of molecules in living and non-living tissues. Okay. There are other ways to think about this. This is called surface enhanced Raman spectroscopy, where you can put molecules on near to the gold or a silver plasmon, and you can get one single molecule being detected in this case. Okay, you can get enhancements to such a degree that a single molecule can be detected by Raman spectroscopy. Okay, so I'll actually end here by stating that time resolved spectroscopy can also be done, and our lab is doing for a long time time resolved spectroscopy, looking at how chemical reactions take place, and we can actually watch chemical reactions, just like this example of a horse being shot at different frames by, this is a classic example by Leland Stanford, where he actually watched a rider, a horse being driven by a rider being imaged in varieties of time scales with a millisecond flash camera, and you can watch how the horse is actually running a race, right? These kinds of things can be done with a molecule as well, and we can actually image a molecule using Raman spectroscopy. That is what we exactly do in our lab. I just wanted to show you one example where we actually watch a molecule react and do charge transfer. This is an example of time domain Raman spectroscopy, where you can sort of get snapshots of an evolving molecule in time and collect this in hundreds of femtoseconds to picoseconds to nanoseconds, okay, and watch the chemical reaction. This can be done in frequency domain based detection, which I do not have time to go through, but it is essentially using pulses, something similar to NMR, which Professor Sarma talked about. And also you can do it in time domain, just like NMR, creating not spin coherences, but electronic vibrational coherences, vibrational beating patterns between two vibrational states, and you can Fourier transform to get Raman vibrations. So these are the ways by which you can collect time-resolved Raman spectrum and watch chemical reactions right in between, in front of you. Okay, so with that, I would like to acknowledge and end by summarizing that I hope I gave you a glimpse of what Raman spectroscopy can do. I went through the idea of what Raman spectroscopy means in very gory detail, but I gave very short glimpses of what it can do in terms of the applications. However, my email is dasgupta@tifr.res.in, which I'm going to write here, and you are free to email me if there are deeper questions that and I can address in the question and answer session now. So if you were to just email me at dasgupta@tifr.res.in, that would be good. But I would like to thank again Dr. Ramesh and and Professor Ayyappan for organizing these series. Of course, one talk on Raman is absolutely impossible to give justice to the entire field. So I'm sorry if I could not cover everything, but I hope I gave you a glimpse of it. So yeah.
Doctor, it was a very scholarly talk. I, being a biologist, I also could gain something from your talk. Thank you very much.
Thank you.
And it was very good. And we have a good training hall and accommodation, everything. We'll be organizing offline physical trainings and workshops also. We'll be inviting you to deliver in Bangalore itself. Whenever it is convenient to you.
Sure.
Please accept our invitation. Thank you very much.
Absolutely. We'd love to do that because it's very difficult to otherwise connect. So
correct.
Yeah. So are there any questions in the chat box?
Yes, sir. There are two questions. We can finish it off now.
Yes.
Can we quantify secondary structures of peptide using Raman spectroscopy?
Yes, absolutely. Can I unshare? How do I unshare? Okay. Yes. Yes. The question is secondary structure, right, in proteins?
Yes, sir.
Yeah. Absolutely. What you can do is you can look at the amide frequencies. So when I talk about peptides, when I think about peptides, right? Peptides are formed because of amide bonds, right? CONH amide bonds, correct? Now these amide bonds have well-defined normal modes. There are certain normal modes that are CO-centric. There are certain normal modes that are NH bending. Okay. Now the combination of the CO-centric stretches and NH bending constitute as an amide 1, amide 2, and amide 3 frequencies. For a helix, the amide 2 frequencies are coming in between 1650 to 1630 wave numbers. So if you have a complete helix in your protein, you will see Raman vibrational frequencies at between 1630 to 1650 wave numbers. Amide 1 will go to 1670 for a helix. For a beta sheet, this is slightly different. I think the numbers, if I remember, is close to 1630 to 1620 for a beta sheet. So these amide frequencies become a marker, and I can give you references on this, that people have used these amide modes to look at secondary structure. How much content of helix is there? How much content of beta sheet is there? How much random turn is there? Apart from CD spectroscopy, you can use this to quantify the amount of structure, secondary structure.
Thank you very much, sir. There is one more question. For structural studies of oxide glasses, being a research student, which one is recommended? Either FTIR or Raman, sir?
Can you again ask the question? Sorry.
For structural studies of oxide glasses.
Fantastic question. Okay, so IR is not going to give you, see, when you are looking at metal oxides, right, and solids, right, the IR vibrational experiment is difficult to do because most of the vibrational modes are in low frequency. Okay, they are typically in the range of 10 wave numbers to 500 wave numbers. Okay. Now, for a regular IR spectrometer, it becomes slightly harder to do an experiment in that regard. So what you can do is you can use Raman spectrometer because you don't have a problem for source radiation. Raman spectra you can collect with any color, correct? So it is easier to use visible radiation and collect the low frequency modes from a Raman spectrum rather than collect low frequency from an IR spectrometer. So I would say my real recommendation would be use Raman, and it is absolutely used all the time for any kind of solid metal oxide, preparation.
Thank you very much, Professor. Once again, I would like to thank on behalf of KSTA, on behalf of participants, and on my own behalf, hearty thank you, sir, for delivering such a wonderful technical talk on Raman spectroscopy, sir.
I'm sorry I could not cover all of it. It was too short a time for me, but yeah.
Down the line, we are planning for future programs also, sir. Then we can have 2 sessions.
Yeah,
on the
I
same
can
thing.
expand it. That's
Yes, sir,
the
yes, sir.
point.
Then we can have 2
Okay.
sessions on the same thing, sir.
Yeah, sure. Thank you
Thank
very
you
much
very
for
much,
Thank you
sir.
very
having
much,
me.
sir.
I also
Thank
thank Siddharth Sharma, sir, for giving the talk, sir. Thank you, sir. I think
Yes, thank you.
till the end of this session, he was here. I think just now they left.
Okay.
Anyhow,
No.
thank you, sir. Thank you, sir, once again.
Yeah.